friend, welcome to this lecture. In this lecture we continue our study of dynamical system and control. So, in previous class we have discussed existence and uniqueness theorem for say non-autonomous system of linear equation and autonomous system of linear equation, or let us recall what we have done in previous class. So, in previous class we have discussed this linear system x dash equal to a t x plus f t, where a t is given by this coefficient matrix a 1 1 t to a 1 and t, a n 1 t to a n and t, and f t is given by this f 1 to f n is a column vector. And here we assume that a t and this vector function f t are continuous on a given interval, and we have discussed the following existence and uniqueness theorem, and it says that if a t and f t are continuous on some closed interval a to b, and if t naught is some initial point lying in this interval a to b, and if norm of eta is less than infinity, then the system 1 has a unique solution phi t satisfying the initial condition phi t naught equal to eta. So, it means that if we assign a initial condition that phi t naught equal to eta, then we have a solution, a unique solution of this initial value problem x dash equal to a t x plus f t and x t naught equal to eta. Here it is x t naught rather than x. So, it is your x t naught equal to eta. So, this solution exists on the entire interval a to b, and so this is the result for non-autonomous system of linear equation. And similarly for autonomous system we have the following existence and uniqueness theorem. The initial value problem dx by dt equal to a x, where a is independent of t, and x t naught equal to x naught, where x naught is the initial condition given at t naught, t equal to t naught, and it is given by x 1 0 to x n 0. Then this initial value problem has a unique solution for every x naught belongs to R n and for all t in R. So, this we have discussed. So, it means that also we have shown apart from this existence and uniqueness theorem, that once we have existence and uniqueness theorem, then we try to find out the solution set. So, solution set is basically solution set is defined as a set V such that it is basically x t belongs to say R n cross 1 such that x dash equal to a x. So, if we define this and we can check that that if x t is a solution, then C of x t is also a solution, and if x t and y t are two solution, then x of t plus y of t also be a solution, or we can say that this set V forms a vector space, because 0 is already there, because 0 belongs to V, because x dash equal to a x has a trivial solution. So, it means that this solution set forms a vector subspace, and we have also checked that the dimension of this vector space is given as n. So, it means that if we want to, so this is up to what we have discussed in previous class, and we can say that once dimension of V is known to us, then we can find out n linearly independent solution of x dash equal to a x, and any solution of x dash equal to a x can be written as a linear combination of the n linearly independent solutions. So, only so it means that this much we have done, but the problem is that once we have some solutions of x dash equal to a x, then it is quite difficult, or how do we know that the solution is actually a linearly independent solution. So, here we discuss next result, which by which we can check that a given set of solutions is actually a linearly independent solution here. So, let us consider the following theorem, which says that let x 1 to x n be n solution of x dash equal to a of x, and let t naught is some real number in R. Then x 1 to x n are linearly independent solutions if and only if x 1 t naught and x 2 t naught and x n t naught are linearly independent vectors in R n. So, please try to understand here this x 1 to x n's are n linearly n solutions of x dash equal to x. So, it means that these are functions basically. So, the linearly independentness of these functions can be obtained by linearly independentness of these vectors. So, these are constant vectors in R Rn, and these are functions of T. So, how the linearly independentness of functions can be obtained with the help of linearly independentness of constant vectors in Rn. So, that is the content of this theorem, and it says that assume that x1 to xn are solutions of 3. So, it means that let us assume that x1 to xn's are solutions, but not linearly independent. So, we assume that these are solutions, but may not be linearly independent. So, if they are not linearly independent, then they exist constant C1 to Cn not all 0 such that this happen. So, we have say that they exist constant C1 to Cn not all 0 such that C1 x1 plus C2 x2 plus Cn xn equal to 0. So, here we are assuming that solutions x1 to xn's are not linearly independent, or we can say that x1 to xn's are linearly dependent. So, we can find out so it means that they exist some constant C1 to Cn not all 0 such that this linear combination is equal to 0. Now, this is true for all t, right. So, if it is true for all t, then in particular we can evaluate at t equal to t naught also. So, at t equal to t naught we have C1 x1 t naught plus C2 x2 t naught and Cn xn t naught equal to 0 comma 0 0. Now, but so this implies what, that here not all Ci's are 0 and still this linear combination is equal to 0. So, this implies that x1 t naught, x2 t naught and xn t naught are linearly dependent vectors in Rn, but here we have already assumed that this x1 t naught to xn t naught are linearly independent. So, here before proceeding this we are assuming that x1 t naught and xn t naught are Li vectors. So, here if we assume that these x1 t naught to xn t naught are Li vectors, then we have a contradiction. It means that the assumption that x1 to xn are linearly dependent solution may not be correct if we assume that x1 t naught to xn t naught are Li vectors. So, here it means that if we assume that x1 to xn's are linearly dependent solution, then x1 t naught to xn t naught has to be linearly dependent. So, this implies that if x1 to xn's are linearly independent, then x1 t naught to xn t naught are also linearly independent vectors. So, we have proved that if x1 t to xn t are solutions which are dependent solution linearly dependent solution, then at t equal to t naught also x1 t naught to xn t naught are also linearly dependent vectors in Rn. So, if solution, so let me write it here, that if x1 t to xn t are LD solutions of x dash equal to Ax, then this implies that x1 t naught to xn t naught are LD vectors in Rn. So, that is what we have shown. Now, we want to show the reverse part of this. So, it means that let us assume that the x1 to xn at t naught are linearly dependence vectors in Rn. So, we want to now go back to, so we want to show the reverse thing, that let us x1 to xn at t naught are linearly dependent vectors in Rn. Now, we want to show that our claim is that x1 t to xn t are also linearly dependent solutions of x dash equal to Ax. That is what we want to show it here. So, if we assume that x1 t naught to xn t naught are linearly independent vectors in Rn, it means that they exist constant C1 to Cn not all 0 such that C1 x1 t naught plus C2 x2 t naught plus Cn xn t naught is equal to 0. So, it means that linear combination is equal to 0 and not all Ci's are 0. So, taking these combination of Ci's, let us form this function, that is phi t equal to C1 x1 t plus C2 x2 t plus Cn xn t. So, once we have such a pair of constants C1 to Cn, then we with the help of these Ci's form a function like this C1 x1 t plus C2 x2 t plus Cn xn t. Now here please observe that each xi t is a solution of x dash equal to Ax. So it means that each xi is a solution of x dash equal to Ax. So in particular linear combination of xi will also be a solution of x dash equal to Ax. So it means that this phi t is also a solution of x dash equal to Ax, because of that linear combination of solution is again a solution. So and not only this, we have phi t naught equal to 0. So it means that if we evaluate phi t at t equal to t naught, then we have already seen that it is equal to 0. So it means that your phi t is a solution of this, provided that phi t naught equal to 0. Now we already know that this system x dash equal to Ax has a 0 solution. So 0 solution is what? 0 is already a solution, such that 0 solution at any point is again a 0 vector. So it means that by existence and uniqueness theorem, it can have only a unique solution. So it means that that x dash equal to Ax with the condition that x of t naught equal to 0, it can have only a unique solution. But if you look at, we have two solution given as x t ideally equal to 0 and phi t given as this. So it means that these two solution has to be identically equal to same. So it means that your phi t has to be identically equal to 0. So it means that this linear combination, that is C1 x1 t plus C2 x2 t plus Cn xn t, has to be identically equal to 0 for all t. So it means that these Ci's are not all 0. So it but Ci's are not all 0, but still this linear combination is equal to 0, proves that x1 to xn are linearly dependent solutions. So it means that what we have proved here, that in first part we have shown that if x1 t to xn t are LD, this implies that x1 t naught to xn t naught are LD, and in the reverse way we have shown that if x1 t naught to xn t are LD vectors in Rn, then x1 t to xn t are LD solutions of x dash equal to Ax. So it means that this x1 t to xn t are LD solutions of x dash equal to Ax if and only if x1 t naught to xn t naught are LD vectors in Rn. And we can say that not that this implies that P if and only if Q. So we can also show that not Q if and only if not P. So it means so negation of this, we can say that if x1 t to xn t are Li solutions of x dash equal to Ax if and only if x1 t naught to xn t naught are Li vectors in Rn. So with the help of this, we have shown that the solutions x1 to xn be n solution of this, and we can easily check the linearly independentness of these vectors if we can evaluate at any given point t naught, and if the vectors x1 t naught to xn t naught are linearly independent, then we are done. So it means that here you need not to check for all t, rather than you can check at one single point t naught, and if it come out to be linearly independent vectors, we can say that our solutions are also linearly independent solutions. So here the problem of checking the linearly independent functions is now reduced to checking the linearly independent vectors in Rn, because it is quite difficult to check that a given set of functions are linearly independent functions. So what I am trying to say is that given any say function f1 t to say fn t, it is quite difficult to check whether these are Li or LD. So it is quite difficult, because here we cannot say that we can write we can have a determinant if it is coming out to be non-zero, then it is Li. It may not be true at all, or we can say that there are say Li functions for which determinant is 0, but still we cannot say anything whether it is LD or not. So here we simply say that the problem of finding the Li linearly independentness of functions is now reduced to the problem of checking linearly independentness of vectors in Rn, and checking Li linearly independence of vectors is relatively easy than finding the linearly independentness of functions. Now here in the particular case when all these fi's are solutions of x dash equal to Ax, this is quite relaxed, and we can say that if we simply calculate the x1 to xn at any given point t naught, if they are coming out to be linearly independent, so we can say that our solutions of functions x1 to xn's are linearly independent functions, and they are solution of x dash equal to Ax. So now it means that we can easily check that a given set of solutions are linearly independent or not. Now let us take one simple example and proceed. So here consider the following system of first order linear differential equation, that is dx1 by dt equal to x2 and dx2 upon dt equal to minus x1 minus 2x2. So we can easily write down this as a system of linear equation. We can write down x1 x2 dash is equal to x1 dash is equal to x2. So it is 0 1, let me write it here x1 x2. So x1 dash is equal to x2 and x2 dash is equal to minus x1. So minus 1 and here it is minus 2. So we can write down dx by dt equal to 0 1 minus 1 minus 2 x, where x is this vector x1 comma x2. And here if we simplify that, if you can look at carefully, then this system of linear equation can be reduced to a higher order differential equation with constant coefficient. So here we can simply say that if dx1 by dt equal to x2 and dx2 by dt equal to minus x1 minus 2x2. So here we simply differentiate this and we can write down this as so it is what you can simply write, say x1 equal to y, you can simply write, and x2 equal to dy by dt. If you write x2 as dy by dt, then dx2 by dt will be what? It is simply d2y by dt square, and equal to minus x1 is minus y, minus 2 x2 is we are writing dy by dt, and it is this. So we can simply write this equation, this system of linear equation is reduced to this single second order equation, that is d2y by dt square plus 2 dy by dt plus y equal to 0, and we can simply solve this equation, and this can be solved using the method we have already say assume that this can be solved, and our solution is given by e to power minus t and e to power minus t. So it is not very difficult. Here we just assume that yt equal to e to power mt is a solution, and we can simply say that it is what? You can simply write m square plus 2m plus 1 into e to power mt is equal to 0. Now e to power mt is not cannot be 0, so this implies that m plus 1 whole square equal to 0. So m equal to minus 1 and minus 1 repeated root we can consider, and we can check that our solutions y1 t equal to e to power minus t is one solution, and second solution you can find out using variation of parameter method, or there are alternative method available to find out the second linearly independent solution. So here in this case we can say that y1 t equal to e to power minus t is one solution, and y2 t equal to t to power t into e to power minus t is the second solution. Now with the help of these two solutions, now let us find out two solution of the system of linear equation here. Now here let us take our solution is basically what? Here our solution is basically x1 and x2, and x1 we have assumed it is y and it is y dash. So we can find out one solution x1 as you take y as a e to power minus t. So if you take y as e to power minus t, then it is e to power minus t, and derivative of this it is this thing. So it means that x1 is one solution of the system given as equation number 4. Now if we take y as this solution t e to power minus t, then your second solution x2 is given as t e to power minus t, and derivative of this, and this you can find out the e to power minus t plus t e to power minus t, and minus 1 will come out. So we can simply say this is nothing but t e to power minus t, and e to power minus t you can take it out, and there is 1 minus t here. So it means that first solution is given by e to power minus t minus e to power minus t, and second solution is given by t e to power minus t e to power minus t into 1 minus t, and so we have two solutions, and now we want to check that these two solutions are linearly independent or not. So for that you can take any point and you check the linearly independentness of the corresponding vectors. So here for the simplicity I am taking t equal to 0, then your x1 0 is equal to what? It is 1 minus 1, and x2 0 is what? it is your say 0, and this is what here you write it 1. So, it means that you can check that 1 minus 1 and 0 and 1 are say linearly independent, that you can check very easy. You write C1 into 1 minus 1 plus C2 into 0 1, and you simply write it, it is 0 0, and we want that this implies what? This implies that C1, and this is C1 minus C1 plus C2, and this is equal to 0 0. So, if you check that we have C1 equal to 0 and C2 equal to 0, the only solution. So, this system of linear equation, that is C1 plus 0 C2 equal to 0 and minus C1 plus C2 equal to 0, this system of linear equation has only trivial solution, that is C1 equal to 0 and C2 equal to 0. So, this implies that the solution which we have obtained as x1t and x2t are linearly independent solutions, linearly independent solution of x dash equal to Ax. So, once we have linearly independent solution, then we can write down the general solution using these x1 and x2. So, we can write down the solution xt as say that is a general solution I am writing as C1 times x1t plus C2 times x2t. So, C1 x1t is given by e to power minus t minus e to power minus t, and x2t is given by t e to power minus t and 1 minus t e to power minus t. So, general solution you can write it down C1 plus C2t into e to power minus t and C2 minus C1 minus C2t e to power minus 2. So, general solution you can obtain using this. So, it means that here in this particular example we have shown that how to find out a solutions of this system of linear equation, and how to write down, how to check that the obtained solutions are Li solutions, and we can write down the general solution once we have the basis of one basis of your solution space. So, here general solution is given by this. Now, what happened here, we have solved by converting this system into this single second order equation, and we know how to solve the single second order equation, but in general it may not be may not be convertible a system of differential equation into a single second order equation. Then how to find out the solutions n linearly independent solution of x dash equal to Ax, that is what we wanted to know now. So, now let us proceed further, and we say that consider first order linear homogeneous equation x dash equal to dx by dt equal to A of x, where x is this n cross 1 vector and A is given by Aij. Here this A is a constant matrix and x is a of course functions in R in functions. Okay. So, we know that the space of solution of 6 forms a vector space of dimension n, that we have already discussed. Now, we want to find out a basis of the solution space, and for that we need to find out n linearly independent solution x1 to xnt. We have seen that in particular case when A is a kind of a simpler matrix, we can convert this system into a single first order differential equation and we can solve that, but in general it may not be true. So, in general for a general matrix A, how to find out n linearly independent solutions, that is the matter of this next few slides. So, here let us take the idea of scalar differential equation x dash equal to Ax, where A is some constant in real valued constant. Now, we know that the solution of this x dash equal to Ax, why we are considering this, because this x dash equal to Ax and x dash equal to Ax, this is a vector value and this is a scalar value. The only difference is that here this can be written as 1 cross 1 matrix. So, here we already know the solution of this scalar valued x dash equal to Ax is given by xt equal to e to power at into c, where c is some real constant. The solution of this system this scalar valued differential equation is given by xt equal to e to power atc. Now, from this can we get some idea to find out the solution of this? One idea is that can we write the similar kind of structure like let us e to power at x. Another way is, can we write down the solution this should be written as in a different manner. Here we simply write that can we consider this candidate x equal to e to power at into some kind of v as a candidate of solution, or another way is, can we consider this that x equal to e to power some constant into v as a solution. So, let us try this first, because it is a quite simpler one, that in a similar way as a solution of 6 we may try exponential function, that is xt equal to e to power lambda t v as a solution, where lambda is a some constant and v is a constant vector. So, v is a constant vector, means n cross 1 size. So, this will be a n cross 1 vector, and we try to see whether this will be a solution of x dash equal to a x or not. So, if we say that, let us first try this, and if it will not work, then we will try this. So, here let us assume that x t equal to e to power lambda t v is a solution of this system 6. Then if it is a system, it will it must satisfy the differential system of the linear differential equation. So, differentiate it. So, if we differentiate it, then we will get what? D by dt of e to power lambda t v is nothing but lambda e to power lambda t into v, and this should be equal to your a of this e to power lambda t into v. So, this is, it means that a into e to power lambda t v is equal to e to power lambda t into a v. Now, e to power lambda t is simply a constant which we can take it out. So, it means that if x t equal to e to power lambda t v is a solution if and only if this condition hold, that is lambda e to power lambda t v is equal to e to power lambda t a v. Now, e to power lambda t is never 0. So, we can simply write that x t equal to e to power lambda t v is a solution of 6 means x dash equal to a x, provided that we have the following relation a v equal to lambda v. So, it means that this x t equal to e to power lambda t v is a solution if this lambda and v forms an eigenpair of the matrix A. It means that the following relation a v equal to lambda v holds. So, we have a proper definition of eigen vectors. We simply say that a non-zero vector v satisfying a v equal to lambda v is called an eigen vector of A with eigenvalue lambda, and this pair lambda and v is called an eigenpair of the matrix A. So, what we have discussed here is the following, that this candidate e to power lambda t into v is a solution of x dash equal to a x if and only if the pair lambda v, this lambda and this v, is an eigenpair of the matrix A. So, it means that if lambda v is an eigenpair, then we can write x t as e to power lambda t v as a solution of this. So, it means that for each eigenvector corresponding to eigenvalue lambda j, this candidate x j t equal to e to power lambda j t v j is a candidate of a solution. So, it means that x j t equal to e to power lambda j t v j is a solution of 6, that is x j is equal to a x. Now, we need to find out n linearly independent solutions. So, it means that we need to find out n linearly independent eigenvectors v 1 to v n, and corresponding to some eigenvalues, say lambda 1 to lambda n. So, idea is to find out n linearly independent eigenvectors, and once we have n linearly independent eigenvectors, then we can write down our solution x j equal to e to power lambda j t v j equal to v j, where j is from 1 to n, all n linearly independent solution of 6. So, it means that the problem of finding n linearly independent solution is now reduced to finding n linearly independent eigenvectors v 1 to v n. So, that is what we wanted to now find out. Now, once we now we want to check whether these are linearly independent or not. So, that can be checked very easily, because since these are solutions. So, x j t's are solutions. Now, we need to check the values at some point. So, let us check the values at 0. So, x j 0 is v j. So, it means that the linearly independentness of the solution is depending on the linearly independentness of v j's. So, if v j's are n linearly independent vectors, then the solutions are also n linearly independent solutions. So, it means that in this case, so it means that if v j's are linearly independent Li vectors for j equal to 1 to n, then we can write that e to power lambda j t v j's are also Li solutions, right. So, this implies this, and once we have Li solutions and Li solutions, then we can write down the general solution as follows: x t equal to c 1 e to power lambda 1 t v 1 plus c 2 e to power lambda 2 t v 2 and so on. So, this is your solutions, right, where ci's are some constants and a real constant, and hence by this discussion we can say that any solution of this system 6 can be written as linear combination of xj, and for this to find out this xj n linearly independent solution of 6, we need to find only n linearly independent eigenvectors of the coefficient matrix A. So, it means that if we want to find out n linearly independent solution of this, we need to find out n linearly independent eigenvectors of A. So, it means that given a matrix A, once we have say V1 to Vn n Li eigenvectors, then x dash equal to Ax has n Li solutions, and it is given as e to the power lambda j t Vj for j equal to 1 to n. So, our now we will focus on how to find out n linearly independent eigenvectors, but finding n linearly independent eigenvectors may not be easy task, and we have only one result which says that under a special condition it may have we have a guarantee that we have a n linearly independent eigenvectors, and that is the following result, that let lambda 1 to lambda k be k distinct eigenvalues of a matrix A, then the corresponding eigenvectors V1 to Vk are linearly independent. So, it means that the crux of this theorem is that corresponding to distinct eigenvalues we have linearly independent eigenvectors. So, this can be proved using mathematical induction. So, let us I am giving you the hint for that n equal to 1, it is quite obvious, because for n equal to 1 we have lambda V an eigenpair, and by definition of eigenvector V has to be a non-zero vector. So, it has to be linearly independent. So, now for n equal to 2, let us say that we have lambda 1 and lambda 2 are two eigen values corresponding to which lambda 1 and we have V1 as an eigenvector, and corresponding to lambda 2 we have V2 as an eigenvector, and we want to show that V1 and V2 are Li vectors. So, here we want to check that C1 V1 plus C2 V2 is equal to 0. We want to show that this has only a trivial solution, that is C1 equal to C2 equal to 0. For that, let us apply matrix A on this. So, A of C1 V1 plus C2 V2 equal to 0. So, this implies that C1 lambda 1 V1, because A V1 is lambda 1 V1 plus C2 A V2 is lambda 2 V2 equal to 0. So, we have a relation C1 lambda 1 V1 plus C2 lambda 2 V2 equal to 0. Now, here we have this equation number 1, this is equation number 2. So, multiply the equation number 1 by say lambda 1. So, we have this 1 implies this. So, lambda 1 times this will give you C1 lambda 1 V1 plus C2 lambda 1 V2 equal to 0. So, this implies that if we subtract these two, then we have C2 lambda 2 minus lambda 1 into V2 equal to 0. Now, here lambda 2 minus lambda 1 is non-zero, because here we have assumed that lambda 1 is not equal to lambda 2, and V2 is non-zero eigenvector. So, this implies that if it is non-zero eigenvector, then the only possibility left out is that C2 has to be 0. Now, if C2 is 0, we can put it in the value here in 1, and we can have C1 V1 equal to 0, and V1 is non-zero vector. So, this implies that C1 has to be 0. So, it means that this C1 V1 plus C2 V2 equal to 0 has the only solution, that is C1 equal to C2 equal to 0. So, it means that for n equal to 2, if lambda 1 is not equal to lambda 2, then V1 and V2 has to be linearly independent eigenvectors. And now, you can prove for n, you assume the for n equal to k minus 1, and you can prove for n equal to k using the similar idea. So, this I am leaving it to you, and we simply say that let us summarize this, and we simply say that let lambda 1 to lambda k be k distinct eigenvalues of matrix A, then the corresponding eigenvectors are also linearly independent vectors. So, it means that if we take this theorem and the previous thing, then we say that if you want to find out n linearly independent eigenvectors, then it is quite easy that if we have n distinct eigenvalues of A, then we can have n linearly independent eigenvectors. So, in this case finding n linearly independent solution is quite easy when we have n distinct eigenvalues of the matrix A. Okay, so let us take one example based on this theorem 5. Example is this: find the general solution of the following system of differential equation x is equal to Ax, where A is given as 1 minus 1 4 3 2 minus 1 2 1 minus 1. So, as we have pointed out, the system, the general solution can be written as once we have since it is 3 cross 3 matrix, we need to find out 3 Li solutions, say x1, x2 and x3. So, if we have 3 Li solutions, then we can write down the general solution. And also we have discussed that that if we can find out, say V1 to V3 Li eigenvectors, then corresponding to lambda 1 to lambda 3, then the solution e to the power lambda 1 t V1 can be treated as x1, x2 is e to the power lambda 2 t V2 and x3 is written as e to the power lambda 3 t V3. Then if V1 to V3 are Li eigenvectors, then x1 to x3 are Li solutions of this system. So, once we have solutions, we can write down the general solution. So, idea is to find out Li eigenvectors V1 to V3. So, for that let us simplify, let us first find out the eigenvalues of this. So, here I am taking the liberty that finding the eigenvalue is quite easy, and you can do that by writing A minus lambda I determinant of this equal to 0. So, as a root of A minus lambda I equal to 0, we can have this characteristic equation, that is 1 minus lambda times lambda minus 3 into lambda plus 2 equal to 0. So, here I am leaving it to you that show that the characteristic equation of this matrix is given by this. So, once we have this, then we can check that lambda 1 equal to 1, lambda 2 equal to 3 and lambda 3 equal to minus 2 are 3 eigenvalue of this matrix A. Now, here we can see that they are all distinct. So, it means that now if they are all distinct, so we have this assurance that the corresponding eigenvector are also linearly independent eigenvectors. So, let us find out these linearly independent eigenvectors. So, corresponding to lambda 1 equal to 1, let us assume that the eigenvector is of this form u1 u2 u3, and we can find out by solving this system of linear equation A minus I u equal to 0. So, here again I am putting lambda 1 equal to 1 and just writing A minus I into u. So, we have this system of linear equation, and this reduces to this, and here again I am assuming that we can easily solve this system of linear equation, and we can have a solution as minus 1 4 1 as a solution. So, once we have eigenvectors, and solution can be written as C1 e to the power lambda 1 t. So, solution is what? x1 t equal to e to the power lambda 1 is 1 here, e to the power t into V1. So, V1 is minus 1 4 1. So, your solution x1 t as written as e to the power t minus 1 4 1. So, that is what we have written, and C1 may be considered as a constant C1. So, if x1 t is a solution, then any constant multiple will also be a solution of this. Now, let us look at for lambda 2 equal to 3. Let us assume that the eigenvector is given by V1 V2 V3, and we can find out V1 V2 V3 by solving this system of linear equation A minus 3I into V equal to 0, and after simplification we have the solution given as 1 2 1, and solution is given by x2 t equal to e to the power lambda 2 is 3 t into 1 2 1. So, this is a solution, and any constant multiple of this will also be a solution. So, x2 t can be written as C2 into e to the power 3 t 1 2 1. And similarly for lambda 3 equal to minus 2, let us assume eigenvector is taking this w1 w2 w3 kind of format, and this we can find out by solving this system of linear equation A plus 2y w equal to 0. Now, A is known to you, you can find out A plus 2y w, and you can find out this as the solution is given by minus 1 1 and 1. So, it means that the solution is given by x3 t is equal to e to the power lambda 3 is minus 2 t into minus 1 1 1. So, here solution x3 t is given to us, and we can write down the general solution x3t equal to C3 e to power minus 2t minus 1 1 1. Now we already know that V1, V2, V3 are Li. How we know? We know by the result, but you can still check whether you are getting a Li solution or not. So you can check that minus 1 4 1, 1 2 1 and minus 1 1 1 is basically are Li eigenvectors. So once they are Li eigenvectors, then the general solution can be written as linear combination of x1 to x2 to x1t and x2t and x3. So C1 minus 1 4 1 plus C2 e to power 3t 1 2 1 plus C3 e to power minus 2t minus 1 1. Then general solution is given by xt equal to this, the following thing will serve as a general solution of this system. So it means that if we have distinct eigenvalues, then we have n distinct linearly independent eigenvectors, and we can find out the linearly independent solutions, and but it may not always be true. So we will discuss more cases of this and how we can find out n linearly independent solution in say coming lectures. So here we stop, we will continue this study in next lecture also. Thank you very much for listening us. Thank you.